Welcome everybody to the Propeller 2 live forum. Today is Smart Pins on the Propeller 2 with Chip Gracey and Jon Titus. Hi guys.
Hey Ken.
Okay, there's one of them, and I know Chip is here because I just saw him. Okay, before we let you two loose, a few minor things here. The Propeller 2 accessory sets, as of 5 minutes ago, we're just coming into inventory. Special note here for Rainer von Deutschland. And also, if you're waiting for a P2 evaluation board enclosure, they're now available for sale on Rich's mom's Etsy's website. So we just had to saw up those boards. Tomorrow morning, I'm going to paste this link into the chat. If anybody is interested in the ESP32 object, we have a small team, Matteo and Riley, who you may have met on our forums, who are going to write this for us. And we're looking at using the standard ESP32 firmware for now. And this would be kind of an AT-style command set. So if people have specific input on this or want to hear what we're doing, you're welcome to join. It's at 9 a.m. Pacific tomorrow morning. And I just put the link in the chat. Okay? So we'll discuss where we're headed. If anyone has certain experience with this, they want to have us here before we start, this is a good place to show up. And thank you everybody for the help on identifying the clicks. We're going to add all these to our inventory, and we aren't sure exactly when we're going to make them available because we'd like to have objects for them first. And it might be that they're not actually available for 30 days or maybe just a tad longer until our new website is launched. They will be useful with this adapter. And then there's also kind of an octopus adapter that you can put on this to connect a whole bunch of them until you run into IO pin conflicts. In a couple weeks, Jeff and Michael are going to talk about Propeller Tool and downloading by Wi-Fi. I'm trying to get this board available first. It's like a cheapy $5 to $10. So you can put our WX module on your P2 eval board and program wirelessly. So I'm hoping to get that available. We'll let you know. Next week, live from Hollywood, Johnny Max, Tao of Spin 2 Programming. This is exciting. There are already 51 people signed up. And John's going to share his tricks next week. So
it's pronounced Dow.
Dow. Thank you. And after that, we got Jeff and Michael as known. And today, Chip and Jon. So turning over to you guys. Thanks, Chip and Jon, for preparing for this today. And Jon, for a lot of volunteer work you've done on the documentation. It's very much appreciated. Okay, over to you guys.
You want to start, Jon, or you want me to?
Go ahead, Trip.
Okay, so I'll talk briefly about what smart pins are in case there's any question. On every pin on the P2 chip, there's a logic circuit which has about 32 different personalities, actually maybe 40 personalities. And what the idea is that the pin can perform a lot of autonomous functions on its own without burdening the processor. So there are a lot of modes which are kind of set and forget, like PWM and numerically controlled oscillator, duty cycle. There's A to D and D to A modes that can run automatically in the background. And the impetus behind this was that forever, I've been programming very low-level microcontroller code. And so I used to implement a lot of this stuff in software. So like with the PIC chips, I did a lot of work trying to make A to Ds over pins, using balance circuits and PWMs and things like this that were cycle timed, even where I'd call off and do something for a fixed number of cycles and come back. It was a real pain to program that way. But I got kind of versed in that, so I had some appreciation of how great it would be to have something to take care of tasks in the background without needing the processor bandwidth. So we have now about 32 basic smart pin modes. And like I said, they do A to D, D to A. There's some PWMs with feedback for building switch mode power supplies. There's asynchronous and synchronous serial. Let's see, there's something pretty neat called a reciprocal counter, which can measure periods for at least a certain amount of time. So what it winds up returning to you is how many cycles occurred and what the total time was. So this allows you to make super accurate frequency measurements without a very long acquisition time. So in this time now, John's been kind of, Jon Titus here has been playing around with these modes, and he's developed some documentation and some examples to kind of teach people how these things work. Now I have this main document that I've written, but the information is all there in a sense, but it's not dressed up with many examples. So some experimentation might be required to kind of figure out how this stuff best works. Anyway, but Jon has filled this in with some documentation and some examples. So Jon, you want to start talking?
Yeah, sure. Let me just say a couple of things to begin. I've been working with Parallax products since the basic stamp came out. A lot of fun working with that, and then with the Propeller 1. But I was not a big assembly language programmer after about 1984. I programmed on other processors in assembly language, but not recently. So getting into assembly language on the P2 took some getting used to, and getting used to the tools that I could use, and also figuring out what these darn smart pins could do. I have found many times that application information from many of the microcontroller companies is overly complicated. You want an application note on how to use, let's say, SPI with a temperature sensor. Well, the chip manufacturers lard it up with a liquid crystal display and a Wi-Fi so you can read the temperature elsewhere, and all I want to know is how do I use SPI. So my attempt was to take the basic documentation and expand on it so that somebody like me could read it, understand what the smart pins do, and have a small example of code that would let them do just that. So my basis was really self-serving, but I thought since I was at it, I would make it in a format that perhaps Parallax could provide within the datasheet or maybe as an application note. So most of the descriptions for the smart pins start off with some general information. They identify the bit pattern. There's often a block diagram. Now, there's a big block diagram I forget where it is, but a big colored block diagram that I found very healthy. And also, I have explained the smart pin commands as well as the read pin, the write X pin, and so on and so forth. I had a lot of trouble with the smart pin 32-bit settings for these pins. So it took a lot of experimentation and some swear words here in the basement lab to get these things right, but did make some good progress. Now I'm going to just share my screen with you. I'm going to untangle some wires. Okay, what do I want to do?
Hey, Jon.
Yeah.
I remember one thing you told me which was helpful. You noticed that a lot of the documentation I wrote is written in this kind of, I don't know, would you call it a passive voice?
Yes.
And you said you identify, though, the way to write documentation is write it into like an active command voice, as if you're telling the person what they need to do to achieve something, which actually is good practice.
Well, I spent about 30 years in the publication business. So let me see if I can just figure out this share. Yeah. Systems preferences. I'm not quite sure how this is going to work, but
should see a green button towards the bottom, and it says share screen. Click on the button, not the arrow next to it.
Yeah, I have to. I'm on a Mac, so I've got to go through some firewall stuff here, I guess. I don't know. Anyway, let's see here.
We've all been having a lot of fun with systems and malware lately, that's for sure.
Well, the other thing was, too, I was taking my brother to lunch today, and we got sideswiped. So, you know, take an extra hour I didn't really have with the police coming and writing up a report. And I had hoped to spend a little bit more time preparing. Is my screen being shared now? You are.
Very nice.
Okay. So this is how I started. I just started writing things down and making them, as Chip said, in the active voice. In other words, talking to the reader. You can do this, you can do that, this does this, rather than saying, this register has 32 bits and it does this. I tried to provide as much explanation in these and combine also the standard pin information that I'm scrolling through here, these instructions and registers and so on and so forth. Chip gave me some input-output bit timing information, and it was in his original documentation drawn with type characters, that is typeface characters. And I tried to clean that up and provide it with some explanation. And then I got into the smart pins and talking about the smart pins and talking about these various operations that the smart pins have in common. And then talking about the various settings, the 32-bit settings, and took the information that Chip had put together and just put them in a form that I could understand a little bit better. Now, there are spots in this documentation where I just don't know what's happening with the P2 and with the smart pins. So this document's available. You can take a look at it. You can make corrections, additions, suggestions, cross it out. It doesn't matter. I'm not sensitive to changes in any sense. So have at it. Okay, here are the 5 M pins and the different modes we can run. And then I talked about the timing and how you would test a pin, because that's important. When I first got the P2 development board, of course, the first thing I wanted to do was light an LED, get something going. And then after I did that, I decided, well, let's explore some of these smart pins. And the pins turned out to be a lot smarter than I was, because it took some real figuring out to get to know them better and to try some things with them. So I just described in general what the pins do, how you would read them, and so on. Now I'm going to skip over this smart pin mode, the first smart pin mode, but his random noise via DAC. I tried to be a little bit more, give a little bit more of an explanation, and then say this mode does such and such. And it explains how you would set a register for sample period and so on and so forth. And then I have a question here in green type. And then I provided a fairly simple example here. Now, I didn't try to do anything ramping up the clock to full speed. I just said, okay, I've got the development board. Let's keep it as simple as possible. I'll work with what I've got. I don't want to add commands that may confuse somebody that they may have to go look up and figure out. So this was the first example. And then I put down here the output at pin 20 appears as semi-random noise, and gave credit to Ariba, who had some information like this posted on the Parallax forum. And then there's another one here. Okay, this is on the DAC output with added pseudo-random dither. And that's generally the format I follow throughout here. A couple of paragraphs of explanation of what's working and how it's working, what the bits settings do and how to put them together. And again, I've put questions in here, things that I don't understand or somebody else can answer. And again, here's a piece of the code. So that was generally the idea throughout this documentation. And it went from about 31 pages that Chip had put together in the data sheet to 61 pages here that I've got. And the 61-page version is the one that you're certainly welcome to look at and critique. And I welcome that, because here again, here's a timing diagram. I've put quite a few timing diagrams where it seems to make sense and explain the values that get used in the PWM calculations and then put into a program. And again, here's the program. Here's another one, the pulse cycle output and code transition output. Another diagram. Some of these diagrams, like this one, this is the numerically controlled oscillator. I thought it would help here. I'll go back in the wrong direction here. Sorry, guys. this is what I came up with, a conceptual arrangement of the NCO frequency mode within the smart pin so that people better understand what the data is doing, where it's going, and how that sum, for example, is fed back. Here's a diagram that talks about the pulse width modulation using the ramp. And another diagram somewhere else in here. Okay, here's the quadrature encoder, again, a wiring diagram in this case, and then a timing diagram that shows how the pulses work, and then a small piece of code. This is periodic measurements and then also free run measurement mode. Let's see what else I've got in here. I did not understand a couple of the timing modes in here. So those are kind of, I guess, in blue type or green type. This is probably one of them. Here are the for periods in X plus clock cycles count time. And where I didn't understand it, there are outstanding questions. I could not figure out the ADC scope with trigger. That had streamers in it, and Chip, you had it set up also to do display, I think, on VGA display on this one. And again, that confused me a bit. So I never did figure out how to get it to work. And let's see, what else we got in here? Okay, USB. I'm not a USB expert. And
the USB thing is very complicated because to operate that peripheral, you have to be mindful of the USB protocol. So there's a lot of prickly stuff that goes into that one.
Yeah, absolutely. There are background reports and a lot of information that you have to provide to the host computer, and you get information back. As Chip says, it's not just like a serial port where you hook them together and they work, although that's the way it appears to users. There's a lot of information that goes back and forth. If you want some information on that, there's a lady named Jan Axelson that has a book called USB Complete. And also the Cypress Semiconductor has an application note out, which maybe I mentioned in here, or mentioned someplace, that will help you better understand what the reports do and that kind of thing. But you could probably just use the USB port that's on the board that's used for programming without having to get into the smart pin. Let's see what else. Okay, synchronous serial transmit. I use the SPI output in 32-bit mode so that I can take a logic analyzer and look at data as results of some of the operations using the smart pins rather than try and print it out. I didn't want to get into using the terminal or anything else. I want to keep the example simple. So I just use SPI to transmit the data many times out, and my logic analyzer picked it up and decoded into the hexadecimal code, which was very handy for troubleshooting and testing. Let's see, synchronous serial, okay. And I didn't really understand the switch mode power supply either. I'm not a power supply designer. Again, here are some scope, or rather, yeah, scope images. Asynchronous serial receive. So that's my contribution at this point. Let me show you what my setup looks like. I'll go get over to another computer. Trying to get on here.
Chip, do you have the chat window open? There's a few questions in there.
John, do you have a radio or TV on in the background?
No, I don't.
Chip, JMG has a question. Or actually, it's a comment. Marcelo, I think it was answered already. What is the max PWM frequency that we can have on those smart outputs? For a three-phase inverter, is it possible to also incorporate dead time?
Let me think about that. Dead time. I don't know what's meant by dead time. I guess that's time that the PWM is never active. You can set the timing up so that you can, fluctuate it between two settings, neither of which are distal. So you could have dead time that way, if I understand what you mean by dead time.
I'm trying to get another camera set up here. I don't know why it won't.
So, yeah, as Jim said, the PWM granularity is the system clock. So, I mean, you could have a 3 clock PWM that has, what would that be? 0%, 33, 67, and 100%. But we don't have any kind of timing granularity that's less than the system clock.
I'm not doing a very good job of getting this second camera to operate on here.
No worries. Marcella, you can also ask Chip the question again in voice or type it again. But I think JMG may have answered it. He's asking about the max frequency for PWM, Chip.
I answered that. It's a function of how many time units you want versus, that are of the system clock. So if you wanted 3, 3, you could have, I guess that'd be 0, 50, and 100%. Now this dead zone thing, you could certainly use, multiple PWM pins. If you start them up at the same time, they're all going to be phase locked. And then you have a whole period. So I didn't mention it at first, but a lot of these things are not just set and forget, but they have kind of a conversational relationship with the processor where at the end of their period, they'll either take in a new value that has been double buffered, or they'll output a value, which you have that entire next period in which to pick up that value or to supply new values. So if you start up a bunch of pins at the same time, you could have them at all kinds of software settable offsets to realize these dead times, if I'm understanding what this is. But the thing is, we have low-level building blocks that you could arrange in many different ways, and you can program in many different ways. The big deal is that it gets the processor out of the loop of having to make a pin high and low at a certain time.
Chip, you were going to describe I got another speaker here. You were going to describe how you would get 16-bit resolution out of an 8-bit converter. You're muted.
You're muted, Chip. Can he not hear us?
I think his internet may have dropped, so I'll try to unmute him. Yeah, he may have vaporized.
Hold on, I didn't have the mute on.
We
Or I
thought,
had the mute on, sorry.
we thought you
Okay,
got eaten by the malware system.
Not yet. I was talking about the 16-bit DAC, right? So we have very low impedance DAC modes, like as low as 75 ohms at 2 volts or 123 ohms at 3 volts. And the low impedance is important to push signals out that are quick and need to have, integrity. So we can use these 8-bit DACs to get, we can oversample them. That's where we toggle between 2 adjacent values, right? So that, let's say you want to output in hex 0080, right? Where that 80 is right of the decimal point, and the 00 at the head, that's kind of like the that's the static DAC state. So what we could do is we could toggle between DAC values 0, 0 and 0, 1 with a 50% duty cycle to realize that 16-bit value 0080. And the best mode we have for this, we have a duty mode, which you can switch at any, you can switch the duty at any time, but we also have a PWM mode where a multiple of 256 clocks should be respected so that it only has 2 transitions, max, 0 to 2 transitions per sample. And what that would do is it would, like, for 0080, it would output 0 for the first 80 clocks, 80 hex clocks, and then go to 01 for another 80 hex or 128 decimal clocks, and then repeat. So it averages over 256 clocks to a 16-bit value. So if you're running that thing at 256 megahertz, you can have, like, every pin on the chip be a 16-bit DAC that updates effectively at 1 megahertz. Okay, let me unmute. So John. Is John still setting up his thing?
Yeah, I'm here. I've got my camera.
Oh, okay, I see it.
It's just showing my test setup. I've got this breadboarding unit here, and I found it, as I mentioned, easy to get the 32-bit data on SPI output. Let me see if I can get my speaker turned down here. Maybe that's what's causing the feedback. Okay, any better? I hope so. So I just use a standard breadboard, and I've got the P2 eval board.
Okay, hang on a minute, just a minute, John.
Scope here, and I've got a logic analyzer that I use quite extensively. The logic analyzer is one of the early Saleh. I think that's how you pronounce it, logic analyzers. It's a nice piece of kit if you want to take a look at a lot of different. Okay, thank you. If you want to take look at a lot of different signals. Now let me just see if I can run something here. No, sorry guys, I thought I could, but that hour spent explaining Bender took more time than I.
No worries, John. I'm sure it's some.
I'm sorry. I thought I had a couple of examples here that I could share with you. I might have one. Let me just see here.
Well, we're just glad you're okay. We know that'll really shake up much more than the rest of the day.
I thought I would have time to get back here.
If John can recover some of those examples, we could also take some questions from people in the meantime.
Now, and it's showing a pulse width modulation output. Nothing special to look at, but it is nice to test the software and eventually see that you've got something coming through that you can then test, and you can change your software around and get things working again. I have been using the Flex GUI. Some of you are partial to other software, but that's what I started with, and I've pretty much stuck with it. Okay, Ken, that's about all I was going to say about smart pins.
I have something I can, and John, I can talk for a while if there's anything you think you can resurrect. Sometimes it's just the pressure of the moment. You can't get this happens to me all the time, but I can go over what I've prepared for a while in case you think there's anything else you can put together. Oh, you're muted.
Yeah, why don't you do that, Chip, and then also questions that we might take.
Let me pull up the chat thing here.
Chip, I have more of a general type question, maybe. So what functions can the smart pins do that would have normally been handled that save you using another cog? when you look at this from a P1 user point of view?
Let's see. Well, okay, let me pull out my document here. Someone has some kind of
Hi,
TV or
I want
radio.
to.
Is that use? No? Okay, so wait a minute. Could it be me? Could I have some video playing in the background I'm not aware of? Hold on a sec here. Oh, maybe something was just, sorry about that. Okay, that was something going on my end. All right. Okay, so what can a smart pin do that a cog might have had to do on a prop one? I'm looking at the list here. Well, certainly handling all these PWMs. And then better than PWM, we have actual analog DACs, which can be oversampled by the smart pin hardware. An NCO was a function that the counter did in the prop one. Well, now every pin has a 32-bit NCO that can output frequency or duty mode.
Yeah, a lot of the P1 counter functionality is in each smart pin.
Yes. Yeah, I started out kind of making counters for the P2, but at some point I figured it would be good just to put the brains in every pin so that, you know, these super high bandwidth background things can happen on their own without any intervention unless some kind of change is needed, like pick up data or give new data. There's also quite a few measurement modes. So there's things that can measure duty cycle, frequency. There's an AB quadrature encoder. I wish I had dug around today to find my encoder. I could have made another little demo for that. But there's all kinds of like ink and deck on pin transitions. There's a reciprocal counter.
Can I ask a question? Chip, on the reciprocal counter, are you able to use that mode to, say, measure the low period of an input pin like we used to be able to do on the P1 counters?
Well, if you just want to measure a low, there are simpler modes for doing that. To really realize a reciprocal counter, what you'd have to do is gang a few smart pins together because you're going to need one of them to measure, let's see, you're going to need one to count time, and you're going to need one to count period. And
Okay.
you can employ a third to determine duty.
Yeah, I only care about the high or low time on a pin like we can do on the P1. I haven't been able to figure that out with the smart pins yet.
Okay, so that's easy. Mode 10000 or mode 10001. So the first one, I'll call it mode 16 or 10 hex. That times every state. So when a pin goes from low to high, it tells you what the low time was. If a pin goes from high to low, it tells you what the high time was. But in case you just want one side, there is a mode that's 11 hex or 10001 binary, and that times the high periods on a pin. But what you'd want to do to count lows is use the pin inversion in the AB selector stuff that's higher up in that 32-bit long. So that can count lows as well as highs. And that's much simpler. The reciprocal counter, what it really does is it allows you to acquire frequency measurements with much less acquisition time than would normally be needed. Like if you want a 1 hertz accurate frequency counter, you need to stare at a signal for 1 whole second and then count your transitions. But with this, you can say, look this long, and then as long as you've looked that long, then as soon as you get that last edge, then retire, you're done. Tell me how many cycles occurred and how many clocks it took to get there. And then you have enough to do the math to get a super accurate reading without a long acquisition time. That was someone who's here today, let's see. I saw his name, Jim, JMG on the forum, Jim Granville. That was his idea. He really pushed for this reciprocal counter, and I reluctantly put it in because it was a lot of work to kind of like figure out and get my head around and everything, but we put it in there.
So Chip, back to the count high state mode, like where you, I forgot which exact bit pattern it is, but it's the one where it's count a high time, right?
Right.
I'm trying to use that to do the equivalent of an RC time input.
Right.
And it works sometimes. It's intermittent.
Okay.
So when I continuously read it, I'll get the correct result a few times, and then I'll get 0 a few times, then I'll get the correct result a few times, and continuously cycling back and forth like that.
Okay, it probably has to do with like a triggering problem. Let's see, if you're using mode 10001, which is called time A highs.
Yes,
then,
that's the mode.
Okay, so what it needs is it needs first to see, and you don't want to just reset it all the time. Configure it and bring it out of reset by putting dir high. And at that point, just read it. If you keep resetting it, you're going to keep throwing off its state. And so it could give you.
I'm just reading it once. So
okay.
I set it up and I read it and then I clear the smart pin.
Okay. So I'd say,
and I wait for it to signal with the in that it's ready, that event occurred, and then I clear it. I do a read pin and then I clear the smart pin state, all in line waiting.
okay.
And it, like I said, it works. And then like the next time around, it'll come in and it'll just return 0, which means it isn't timing anything.
Right. I think what's happening is it's not getting some sort of initial state. Maybe it wants to see, if it's going to time highs, it wants to see a low to high transition to begin its count. So maybe it's never seeing that sometimes. So there it is, reset at 0, waiting for that initial event. It doesn't come, it gets read, and then you see 0 rather than a reading. I think something like that.
So the pin is already high because before I call the RC time function, I'm charging the pin because it's using the light thing with a capacitor. So you set the pin high and then let it float and then count the time that it's high till it drops.
Okay,
so you're saying that I need to set up the mode first and then push the pin high so that it'll see that transition.
Can I interrupt you?
What's that?
Yeah, this is John. Can I interrupt for a second?
Yeah.
There is an example of that in the revised instructions or the pin documentation, and I'm running it now. And I can move my camera, and I'll show you exactly what it looks like on the logic analyzer, if you like. Want to see that?
Yeah, I'd like to see that. But also sure. the key question is, if it does need to see the low to high transition while the smart pin mode is already active, then that answers the question. I can just rearrange the order of operations, because right now I'm pushing the pin high and then doing the smart pin mode. And that's because on the P1, you would push the pin high and then set up the counter, and it would just count while it was high until it went low. It didn't need to see the low to high first.
Yeah, this wants to make an accurate measurement. So it wants to see that initial edge into the state of interest and then the edge out. And so because it's not seeing that initial rise, it's giving you back 0. But which you understand.
Hey Roy, is this on the B or C version?
It's on all of them. That logic hasn't changed since A.
Okay, all right.
Yeah, so that's kind of where the documentation needs improvement to cover things like that.
All right, what I've got on my logic analyzer now is an upper trace that is the SPI clock, the SPI data on the second row, and debounce switch contacts on the third row down. I'll just expand this so you can see the timing. Okay, it's starting there and then ending on the negative edge and putting out the results on the SPI. And the example does the same thing that's in the documentation. So you can strip out the SPI and see exactly how I've got that pin configured in that example. Okay.
Okay, so that's
excellent. I'll look at that in the docs.
Yeah. Okay.
Thank you, John.
You're welcome.
Jim asked, why would someone want semi-random or other dithered added to a DAC value? Okay, so we have two things where noise are added to the DACs. One, there's a pure noise mode where 8 random bits from the pseudo-random number generator in the core or in the hub can be output, and there's like, I don't know, 128 of them or so. So in different combinations, they can be output to pins. So you're never going to see the same noise on any pin. There should be no correlation between noise, but it's just meant to be just a random noise source if you need that for any reason coming out of a pin. So it'll be, you know, either a 2 volt or 3.3 volt range signal. And then the other place where we use randomness is for the DAC and the 16-bit dither noise mode, where we take those 8, so we have 8 most significant bits drive the DAC directly, and then the lower 8 bits can cause us to go to the next value in the DAC, step up. So what we do is we take those lower 8 bits, add to them every clock an 8-bit random value, which will cause to carry out periodically that will be in proportion to those 8 LSBs. And then that causes the DAC to step up to the next value or stay at the same value. So it just toggles between 2 adjacent values. And that's the nice thing about that is you can change that 16-bit output value anytime you want, because there's no timing frame to the whole phenomenon. It's just all random. Whereas with the PWM, you want to respect that 256N frame size so that you don't interrupt the the dithering, which is locked to a 256 cycle frame. Let's see.
There's a long discussion, Chip, from Dwayne about brushless motors encoders.
Okay.
I don't know if you want to read it from the top or ask him.
Let's see. Okay, I'm at the top. I don't see Dwayne here. Let's see. I'm not seeing...
Question begins with, can the Quaduture encoder smart pin be used to read a 3-channel encoder like the ones used on brushless motors?
Okay, a 3-channel encoder. So I'm not sure I'm familiar with that. I'm thinking of the A-B type where you have 2 signals and one edge leads the other. I don't know what a 3...
Dwayne further commented, the brushless encoders are 120 out of phase. They're called A and B and a 3rd letter, I think U. All 3 are used in brushless with sensors.
Okay, so if I had known about that, I would have put that in, but I didn't. So the Quaduture mode is not going to work with all 3. You could probably hook 2 in there and get some kind of reading, but you really want 3, I see. So here's the thing though, the chip can run at like, we run it on our desktops at 300 megahertz. So 3 nanoseconds is an awfully high sample rate. If you wanted to do that in software, you could still monitor a 3-input encoder, do it in software, and I think you could probably run that loop at a couple of megahertz, which might be faster than what you need anyway. So you could do that in software, but it would cost you a cog to handle the software. I see his comment now. It's near the end. Yeah, so when we make a change to the logic of our chip or make a new version, then I'll incorporate the three-phase encoding.
And Chip, there have been a couple of requests for diagrams, block diagrams as figure additions for smart pins.
Right. Yeah, I know, I need to make those. Although Evan H. made a pretty good one. I think it could be discovered on the forum.
Now, Bob asked something interesting. Can you make a smart pin sample for audio pitch detection?
Yeah, of course. Yeah, so I've always liked you know, signal synthesis. I love audio stuff. So the chip has the facilities for digitizing. You can use the DACs in very sensitive mode, which are AC coupled in that case, to do AC type ADC. And you can run that through the Goertzel filter, although you don't really need a hardware solution. If you want to do pitch detection, I would just probably take, instead of 1-bit samples at the clock rate, I would take, you know, maybe 10 or 12-bit samples and then do that in software and do an FFT, or at least a slice of an FFT, or maybe 3 slices so that you know what side of things you're on. But you could certainly do accurate pitch detection. And I want to add a debug display thing that is like a needle meter. Maybe I'll get to that tonight. But that way you could just feed that thing, and if you wanted to put 0 at the top, then you could show you sharp or flat. But certainly the chip's capable of doing all that kind of stuff.
Well, I had that working to some extent on P1. As you know, I want to measure pitch from this very badly, which has a couple pitches in each tone. And I know others are interested in the same thing. I think, though, what you said, I would need examples, Chip. I worked with examples from others last time, so maybe we will get there.
Right, right. Yeah, there's a lot of stuff I want to do that really can't be done on Windows using any display. Like, it would be nice to have like some kind of monitor you could put in a room where you're playing drums, and you could work on your drum roll so that you can actually see where you're faulting. Because it's a lot easier to make a pulsing drum roll than a very smooth drum roll. But for me, it's hard to know. I need to see where my error is so I can see where to correct it. And we can do that on a display pretty easily. But anyway, so there's a lot of stuff I want to do like that that involves the chip, that also involves very low latency output to monitors and things. Because Windows, you know, there's just a lot of latency. It's good for batch processing stuff, but it's not that good for live processing. So yes, we need block diagrams in agreement. Okay. Okay, so someone asks, is there a smart pin? Thomas Allen asks, is there a smart pin ADC mode for current input? The short answer is yes. We have these magnification modes that really just kind of devolve into current mode inputs. So what you would do is AC couple your signal in. The pin will bias the voltage near its kind of 0-1 trip point. And then as excitation comes in through a capacitor, it will cause some deflection, which is only going to be like maybe plus minus 20 millivolts full scale. But that will cause the DAC to go all the way from 0 to 100% duty. I mean, excuse me, the ADC. The ADC will do that. So for things like automatic gain control for photodiodes, we have the hardware in every pin to do that kind of thing. And it works for microphones like as well too, in the same way. Can I make a smart pin audio for sample for pitch detection? Yes, I want to get into that soon. There's a lot of synthesis stuff I want to do because not only do we have A to D and D to A on every pin, which are pretty good. I mean, audibly, they're very quiet. I don't really hear any noise. You know, it's not like maybe audiophile quality, but it's pretty decent. And then we have in the chip, we have this Cortex stuff for doing all kinds of log to exponent and back, which is important for musical scales and for amplitudes. And then we have all these circular functions in the Cortex as well. So we can do just tons of really easy processing to do all kinds of signal synthesis and resolving signals, measuring them. Could you make a pitch to MIDI? Sure, that's possible, yes. Let's see. Okay, that's the last comment. You guys want to see, wait, let's see. No one's display further posting.
Chip, I have a question about the intent of the Google document, how open it should be.
Okay.
Okay, right now it's set anyone with the link can view the document. All right. What was your intent? To have it open for editing or commenting?
No, just commenting.
Okay, so I'm changing it now. Anyone can now comment with it.
Okay, yeah.
So Stephen was having trouble. Stephen, now you should be able to comment on it. And so those who are requesting edit access, well, the request is going somewhere in our office. I don't know who started the document. It wasn't me. Someone will have a bunch of email. Thanks.
Okay. Now, Gerald Gorman said, he's the guy that had the really fancy data visualizer last week. So he said let's see, that he downloaded the debug display code that was posted last week. He's ported it to C++. It's up and running, but it's currently being debugged. So I gotta give you an update to all that. What I might do is just make the whole thing standalone, because I realized there were some problems with the way I was doing the log scaling. I had problems with the fact that log, you can't have, was it log 0? You can't, there was some limitation with log. I had to like add 1 because I wanted the scaling factor, but I didn't want the problem around 0. So I changed the way that works and it's all straightened up now. So I need to post that. But what I can do is probably just make the whole debug thing after a little bit a standalone program that anybody could just invoke and then open with a serial port and use. And I'm also going to add the ability to open and close windows so that you can really use, you can drive that thing to do all kinds of displays.
Chip, may I ask a quick question? This is Steve. You had posted the source, he's working with it and converted it. Would you be willing to just keep an updated source as you make these changes available on, say, a forum thread?
Oh, you mean would I be able to do that?
Just instead of sending it to one person, just put it up on the forum thread. So I actually wanted to port it to a different language as well.
Okay, yeah, that's what I did. I posted my code to the forum and then Gerald got it and he converted it to C++, and now he has that version of which I don't know what he intends to do with it. Maybe he'll make it open source. Maybe he'll make an app out of it. He can speak to that.
Yeah, I'm sorry, I looked there, I didn't see it.
Okay, where did I put it? It was in a discussion thread that was kind of transient. It came up, and so I posted it there, and I don't remember where I put it.
Oh boy!
But what I'll do is I'll take what I've got in the next couple of days, and I'll repost it into the main thread, the very top thread in the whole P2 forum.
Right. So, that'd be perfect. Thank you.
Yeah.
What I'm contemplating is I'm going to be starting to look into the P2D2 as a Raspberry Pi hat. So I've got a wonderful signal processing front end with the P2. I suspect, and what I'm theorizing is that I can probably make that whole debugger sit there and run on the RPI itself, listening over the channel. And that's a trivial thing for me to whip up in Python. I just need to see your logic. And so I thought I'd try that if you have the code out there.
Cool. Yeah. All right. Let's see. Yeah, Samuel Lorenzo says we need to describe the VIO pins. Agreed. Yeah, we need some electrical specification. We haven't really done that yet. Hey, Lachlan had a really cool idea, or tubular. This debug thing that we have going, what if we added file I/O to it? So that now the P2 at runtime can access the PC's file system and create files, write data to them, and then read files from the PC. And the funny thing is, if that gets ported to any other platform, it can kind of turn any machine into, like a data display device for very low-level hardware, and a logger and a file system. Because really, what we have in our PCs that's very useful, but comes with all kinds of baggage. There's a file system, there's a display, there's a mouse, and a keyboard. And for a lot of things we could do, that's all we need out of the system. But the OS is pigging up the picture, inhibiting everything you'd want to do. Our kids got a Chromebook from school. The school gave them Chromebooks for this distance learning program. And it's completely Googleized. You can't get off the Google bandwagon. You can't go to DuckDuckGo. And Google's been, necking down its search results to what it wants you to see for so long that it's like a completely managed experience. But to me, I would just like to use the keyboard, mouse, and display and speakers and file system. And internet access too is a nice thing. Okay, should I show what I prepared?
Certainly.
Okay, so I'm going to share my screen here. I've hooked up a special little monitor that I think it's in like some low-res mode. And let's see, here it is. Okay, can everybody see this?
Yes.
Okay, so this is the P2 program, right? And this is a little bit of code I wrote today. And I thought, and here's a new display I made. It's called Logic, right? So you just call it up like this. And it has some things that I overrode. I think that it naturally has like 64 samples spaced at 8. So I overrode that. I made the text size 20 because I wanted it to be big, because the height of this is a function of the font here, right? So it's going to be otherwise just whatever I put in my editor at the time. But by overriding it, I could make it nice and big if I want it. And then I gave it two symbols. So the way this thing works is the first thing you put here is the first label that appears. And I could put a number after that. Like if that had 8 elements, I could go like that. And it would show 8 from the LSB up of a 32-bit chunk of data received. But I just have 2 single bits, so I put, TX and in. And then what I have here is a little spin routine here that starts off, and it does some assembly language. And so what I wanted to do is, in order to show a smart pin, I thought it would be neat to have the streamer capture the data live at like, here we are, 200 megahertz, right? Just capture it live, and then into a buffer, and then later down here, throw that, output that buffer to this debug window over here, and then it declares this thing up here and sends data to it. So it's a way to, it's like a scope that doesn't have to be electrically connected to anything, and it's real time. I mean, it's not real time, but it's full speed. So the way this thing works is these lines here, these 3 lines, they set up the TX pin for asynchronous serial output. And this 2 here means I want 2 clocks per bit. I could have a big fractional, bit time too. I just wanted, so that means that if this thing's running at 100 megahertz, it's going to be outputting new bits at 100 megahertz. And then this says I want 8 bits, so it's going to be like 8N1 configuration. And then here I turn the pin on. And then down here in these 2 lines, I kick off the streamer. I tell it to start, writing, get ready to write data to buff address without limit. And then this is the mode, this value here. I just looked at the main doc file to get this, but this sends, it captures 8 pins, and it does a WF byte, write fast byte every every time it executes, so every clock in this case, because the default clock rate is the full speed of the clock. So, and then here I'm saying record 200 samples and then quit. And then this is not used, so it's just nothing. So I configure the pin, pull it out of reset, then I get the streamer going, and then down here I send data. So I'm just kind of manually, I'm not using interrupts, or I'm not really looking at the in state. I'm just saying, okay, I'm going to write a value to output, which is I. It starts out being 5. Then I have to wait like 3 clocks before I can start polling. And then here I poll until it's done. And then I loop here until I've output 5 bytes. And then this instruction just waits for the streamer to be done. So the streamer should be the last thing going on. So I wait for the recording to be done, to be complete, and then I get out of here, and then I just send it off. Down here, I just send it off to the terminal. And I had this set up using an array, so it did it all at once, but I realized I have to increase my buffer size from 256 bytes to probably like 16K bytes to allow a good amount of data to come out. Because right now, this whole thing's limited to, message sizes of 256, which isn't all bad, because really, practically, you don't want to hog up the serial port for an inordinate amount of time, because there are other things that might be trying to send out debug messages too. So anyway, this is light duty on the port here. So when this thing runs, boom, there, so you can see the result. So it made a recording, right? Now, I use P25 as the output pin, and then I put a little jumper on at my board between P24 and P25, because if you were to read P25, what you're reading is the acknowledged state, or where in is raised when a process is done or something's ready for data. You're not actually seeing the actual serial data come out of the pin. So by jumpering it to P24 and then capturing P24 to P31, but then only looking at the the 2 LSVs of these bytes over here, we're seeing here in the TX line on the scope on this logic display, we're seeing what was actually being output. And then on the in, we're seeing what was coming in from the serial pin that is telling us when it's ready for more data. So when this is high, it's ready for data. When it's low, no, wait a minute. In high means it's busy. Because it's double buffering, you can see it's not very busy. So we wait here. Is that right? Because why is it holding off so long here? Anyway, what it does is it outputs a byte. And if you look at this here, can you see where my cursor is? Okay, so you see that's the start bit, right? And the first thing it's going to output is 5, which is backwards. It's 1, 0, 1, and then all zeros up to the stop bit right here. And the reason there's such huge gaps between these serial things, normally they'd be very stacked together, but there are gaps now because it's running at like, it's taking 20 clocks to send out, because this baud rate is, unusably high. It's like 100 megabaud. So it's using, you see this interstitial space from here to here is when it loops around and gives it the next byte to output. But I could change this thing around. Like if I want to say, let's change the, let's go 3 clocks, right? So 3 clocks per bit, and you can see that spread it out. And if we go 1 clock per bit, whoops, hold on. Let's see. No, I'm still 3 clocks. Hold on here. Okay, that's weird. It's not saying, why is it not? 1 clock per bit doesn't seem to work for some reason. Maybe I'm not getting out of a polling loop or something. Okay, I'll put it back to 2. Oh no, wait, something's happening. Let me try again. Well, that's weird. It kind of disappeared. Okay, so I'm not sure what that's all about. But anyway, there's 3 clocks per. So this just sort of demonstrates how you can use the streamer in conjunction with the the debug display modes to capture data that was happening very quickly and see what was going on without even really needing any normal test equipment. And I wonder if I've come up with any other, let's see, recently I made another thing, log scope, is this it? Let's see, what's this doing? Okay, so here, this is using a trigger function. So I have this down here is my, well, here's where I configure the logic analyzer. And here I set up a trigger where I'm saying, use a mask value of C3F and then compare to C00. And when that's true, that's a trigger event. So then down here, I feed it data. I'm feeding it, the 8 LSBs are a counter, and then we have 4 random bits, and then we have a bit from the system counter. And so it's triggering when all these lower bits, these 3F, these lower 6 bits are all low. Never mind these 2 upper green bits. It ignores those. And then when the top 2 random bits are high, that triggers. So the thing just silently gathers data until it hits a trigger condition, and boom, it updates the display. But we could make much more complex triggers that have greater sequence to them. I could just, add that in. But anyway, this is a new little logic display. It's just called logic. So that's about that. That's all I have for that. Okay, one other thing. Let's see. I had something, log scale. I did some improvement. Now this is only going to update after it's done with the data, but I had some initial problems with the log math that I was mentioning, but I've got that straightened out. So see, it does center around 0, 0. So what this is an XY display with logarithmic scaling. And before I had some dots here that weren't there. But anyway, this is cleaned up now. So I just posted on the top thread in the forum a new version. It's V34W that has all the stuff in it. All right, now, if anyone, what we did last time when we were done, we kind of just ended things, but some people said they would have liked a few minutes to speak amongst themselves. So we can do that for 10 minutes if you guys like. If any of you would like to ask me or each other any questions, you're welcome to. So I'll turn my my mute off. I'll turn my mute on for now. If anyone wants to speak up with anything, or you can type something into the group chat too.
Hey, Chip, just downloaded W version, and it went through fine with Windows 10. So we're good to go there.
Oh, okay, good. So Windows didn't delete it yet, huh?
It didn't even cough on it.
Okay, it probably won't get to it till tomorrow or so.
Yeah, yep.
I think Peanut has been declared non-essential.
Hey, Chip, can you hear me?
Yep.
Jim Granville has a question. He wants to know if the background can be changed on the debug windows.
Oh, yeah.
For background color, for purposes of grabbing images that you've output and pasting them into documentation.
Okay, yeah. Let's go back to something that updates pretty quickly. Like let's see, this one here. Okay, so what I can do here is where I declare this. At any point in here, I can say, let's say we want white, right? So now if I run this, wait a sec. Why is it That's strange. It keeps, and you can also override the colors too. There's a file called, oh, it's in the thing. It's something like debug display modes, and it has all the syntax for these various modes. But you can override, like, see for TX, let's say I want TX to be blue. I can put right here. Oh, wait a minute. Oh, you know what? I have to put one oversight. One channel. Okay, so there I over rotates, but it looks like I made it black. But oh, because 33. I'm at FF. So here we go. There. So you can you know, override any kind of background or color. So if you're looking to print something on paper, maybe this is more friendly.
Chip and Jeff, do you guys see having this incorporated into Propeller tool by October?
Oh yeah, there's really nothing to do. We just have to add it to Jeff's app and put a few hooks in. But all the code that makes this happen, I just give to him as some Delphi files, and he just has to launch it when it's, you know, when someone does a debug download.
Tubular's asking how you captured the MP4 video you posted the other day showing moving data.
Oh, okay. So I found some program. I think I had to pay like, maybe it was $49. It's called Flashback Pro 5. So I'll type that here. And it's, let's see, Flashback.
Snagit's a good one too.
Yeah, this thing makes really compact MP4 files. Like that first one we did with the XY scope, it was like 264 kbytes or something for like 13 seconds, which is nice. That's about how it should be. Oh, hey, one thing I can show here, let's see. I think this is it. Okay, so we have a new Goertzel board that Von Sarvis worked out. It's got, let me see if I can show you a picture of it. It's way better than the first one that we sent out with the parts kit, or, you know, the add-on boards. This thing is super linear now. We had problems with the other ones being really persnickety, but you can see I can like draw squares on this. And we also have, let's see, I'm going to take my camera here. Let's see, where do I, where's my mouse? Where's my, let's see. Oh, okay, stop share, hold on here. Okay, so you can see this, right?
We need to get you a document cam, Chip.
Yeah, this won't really focus. So you can see these four little kind of annular segments are on the outside. And then what we did is we put the sensor pad on the back, you know, through the FR4, you can see that. And that works really nicely because it gets rid of that overcoupling that occurs. See, now I can, it's just much better. So this thing it's now behaving like, you know, I kind of hoped it would from, you know, when we first worked on it. So we also have the Goertzel thing has the ability to output not just 4 phases. Like right now we're doing 0, 90, 180, 270, but we can also do 0, 240, let's see, how to go, 0, 120, 240. Because what the principle behind this thing here is that really it's a mixture of a circular set of phases. And then the question is, what is accumulating on that center pad? And we can do this with 3 pins now instead of 4. But so Von Sarvis is working on a new board that uses 3 rings instead of 4, and then we have 1 pickup. So we can actually fit the whole thing into 4 pins. So on one of these boards, we'll have 2 of them, which are going to be about 1.5 inches of interior area. So they're going to be nice and big, and you can move your fingers around on them independently. And so he'll have that prototype probably a little later this week. But the application for that thing, though, we don't really know. I mean, you can use it as a pointing device, but it has a lot more potential than that. I'm just not sure what it is. And we can also, instead of just inputting on 1 pin, it actually inputs on 4. And for each of those 4 pins, you can say to ignore that pin, add that pin in, subtract that pin. So we can do all kinds of funny differential stuff that we haven't even played with yet.
I haven't seen the files for that Goertzel board, but we'll order them, and we found as soon as we get them.
Well, we're going to do a proof of concept first, make sure that the thing really works right. And then once that's all done, it'll become a product.
And we found a 3-day turn new company we're qualifying that's really quick, also in Taiwan, that we're going to use for that.
Good.
Hey, Chip.
Yeah.
Earlier I was wrong. I'm using 10001 for the mode, not 10010.
Okay, so that's the time A hides.
Yeah, and it seems to work, like I said, most of the time, but it intermittently just fails and gets a 0.
Yeah, what's happening? It's not getting some kind of initial transition.
Well, the way it's described, it sounds like it should just count how long it was high previous to a high to low transition, and it shouldn't care about seeing the low to high in front.
Yeah, the documentation says that just on each high to low transition, the previous high duration is placed in Z and N is raised.
And like I said, it's working most of the time. It just intermittently doesn't.
And you know what's weird? You're saying you're getting 0 sometimes when you read it?
Yes.
That's really interesting because during reset, the output, the 32-bit output register is held at 1. So and then it's incremented thereafter.
Well, so, I'm probably getting a 0 because I'm dividing the result to get it to be, it's in units of the time. I'm porting simple tools, the simple library stuff, and they scale the number even on the P1. And like I said, it works. The example I'm using is the sense light example, and it's using a little RC circuit, and it works better when I've blocked the light, so it takes it longer to transition.
Okay.
It never fails in that case. It's only when I'm allowing light to reach it, and it's supposed to be getting fairly small numbers, a few hundred to 1,000, which it's displaying, but then it occasionally will just output a 0 instead. And in that case, it's probably that 1 being divided down to 0. But
right, yeah, it's losing the 1.
It's like it counted no high time, even though there definitely was high time on the pin.
Okay. I'm looking at the Verilog code for that thing right here, and it does a clear, and it does that. It clears it whenever A changes, and then it counts and then it's done when it goes from high to low. So it does need an initial edge. In this case, it would be like, that'd be a positive edge, right? It wants to see the positive edge to start the count. So the documentation is not really, needs to be fixed.
So that makes it not compatible with the exact same thing on a P1, because the P1 will just count while it's high, it counts, and then it returns the count after it transitions to low.
Yes.
And so I can't implement RC time the same way.
No, but let me look here at these other modes. So we have these like time X highs. I'm looking to see if these things, most all these modes are looking for edges, because the idea is it wants to get a comprehensive measurement, not just starting off and then, you know, until it goes to the other state. They all seem to be looking for edges.
Because the idea is that the pin is already high before I even tell the smart pin to go.
Yeah.
And I want it to count that high time until it transitions to low.
I got you.
And I can't really change the way RC time works, because you're setting up of the pin to charge your device. You might need different amounts of time for how long it should stay high before you then let it drop and count it.
Right.
So it mostly works. It's just when it's short, it's failing sometimes.
Right. It's not seeing the edges that it wants. So there might be, I'm looking at the other counting modes here. You might experiment with the, let's see, time, no, not that. Time, A input, high states.
Remember, in the P1, we could charge the cap and then clear the phase accumulator and then allow the count to go until the pin dropped. With the smart pins, we can't do that, right?
It doesn't, I don't think we can. I'm looking at this. There might be a mode that you can get to do that. You have to kind of look at all these other things. So there are quite a few counter modes. But see, if you're trying to convert, Roy, ultimately, are you trying to convert like a capacitance into a number?
I'm doing, the example is the RC time example that you guys made for Simple ID and Propeller C, where it's trying to emulate the RC time
curve.
Yeah, so what it's doing is it's charging a pin by setting it high, waiting a little bit, and then it sets up the smart pin to count high to low, to count until the high to low transition happens.
Right.
So it's a charged capacitor that eventually the pin will go below the threshold for a high to low.
Yeah,
and
to make
then
it
you
work,
take that time. It's the same thing you would do for a ping, right? If you want to read the ping, you charge it and then wait, right?
Right.
Or other devices.
So what you'd have to do to make this work is you'd have to like have the pin low, enable the thing to make, use that mode 10001, and then get the pin out of reset so it's ready to go. Then lift that pin high for so long, and then let it go so it falls the other direction. And that would give it both edges that it wants, but you'd have some like base time that you'd have to subtract, which is your charging time.
Again, that means that we can't implement RC time the same way that it always has been implemented.
Yeah. It's not going to work then, unless.
So I can't port the Simple Tools RC time to match P1 functionality.
But Roy, is that necessary since we have ADC smart pins?
Yeah, maybe I can just read the ADC and do it all in software, but that means then I have to sit there with a cog spinning, reading it, instead of letting the smart pin do it and then waiting for the event.
No, you can set up a smart pin as an ADC. Oh, I see what you're saying. Yeah, because you want to have that circuit.
Oh.
Yeah.
I know how you can do it. here's what you do. Change, okay, you know you have all those upper bits that select and invert what is the A input to the pin?
Uh-huh.
Toggle that invert bit so that it sees a 0. You create the 0 when you let the thing go down. So I think it's the, let me look at
So you're saying start the smart pin mode and then toggle the invert bit once,
right,
and then let it go?
Right, and that'll let it see. Let's see, I'm looking, whoops, let me see, I'm trying to find these bit patterns here. Here we go. So, yeah, so for A, so it would be, so the MSB of the right pin value, if you were to make that 1 briefly and then make it 0, after you've let the pin out of reset, right? So the pin's running, it's ready to count, toggle that bit twice, and it would then kind of arm and be ready to register that negative edge later on.
Okay. I'll see if I can figure that out. So do I, because I normally just set that bit with the right pin, so would I just right pin again with a new value?
Yeah, so
and that won't mess it up, because I thought right pin would set
no, as long as you're not changing anything, I don't think it's going to do anything. I was looking at it the other day because I was worried that maybe it would affect something, but it doesn't affect any kind of smart pin stuff. So you're fine there. So what you would do is you would initially configure that pin with the MSB set, right?
Right.
And then very quickly clear the MSB and then do another right pin after it's all out of reset with the DIR high. And then you'll fake it out, and then it will think that it saw a 0 briefly. And then it will see the 1, it will start counting, and then when it finally goes down, it'll give you your final count.
Okay, I'll try that in a little bit.
So Chip, I'd asked about the ADC and possibly using it for current inputs, and that's closely related to this RC time question. And I'm really talking about DC levels. So I've got a photodiode on the P1 directly connected to a pin, integrating it on a capacitor, and the feedback comes through a precision resistor. So I'm measuring that current, DC current, with fairly high accuracy, and at high gain. So it's a similar way to solving the problem of what the current is, not what the capacitor value is, for DC measurements or for ratio between a couple of different currents. But without having that second pin available to attach a precision feedback resistor to, how am I going to do that on a P2?
Let's see. Okay, let me get my head around your question. It's kind of complicated. So
not really. It's just measure the DC current photodiode connected to the input pin of the propeller. If there's no light, it's not drawing any current, and everything's at 50% duty cycle on the, roughly.
Okay.
But then there's current, and you're pushing it up, or you're pushing the duty cycle down. So you're measuring that DC current.
Yeah, and are you trying to measure like a DC level, or do you want to measure some AC phenomena?
I'm specifically talking about DC current here, quasi-static currents, like you're scanning across a sample, a biological sample at a very slow rate, and you're looking for absorbance bands. And so there is an AC component, but it's preferable to do the subtractions in software. And sometimes it's a ratio between two currents. So there's a DC canceling current, as well as the current that comes from the sample itself. And I'd like to have the canceling current come from a very slow digital to analog signal that modifies the canceling current at a very slow rate.
Gotcha. Well, let's see.
So can the P2 do the old P1 trick of having a second pin to, do the old, the feedback?
Well, sure, yeah. You could do it to 16-bit resolution hands-free.
Mm-hmm.
it could be, it's going to come out of the pin at, you know, between 75 and 990 ohms, depending on what mode you select. But you can increase that if you need to with the resistor.
But are those polysilicon resistors, or?
Yes.
So they're not going to be very stable, are they? For measured current, the resistor value has to be stable.
Okay, well, they're ratioed. They're ratioed. So
they're ratioed for DC voltage measurements, but there's no ratio. You're playing an absolute current against an unstable resistor in that case.
Yeah, I don't know. Maybe you'd want to put the resistor outside and use PWM and a capacitor or something.
Well, that's what the P1 does, basically. Yeah.
Yeah, then you can control the impedance with a known good resistor. And then you switch rail to rail, who cares, right?
Right, okay. So that's done through the cog, though, not through a smart pin, right?
No, well, no, in this case, the smart pin can run the PWM. You have 16-bit resolution there. And
but it takes some software to control the bias voltage that we're working with. And
yeah, a couple lines of code.
Yeah, that should work.
I think it would just be a couple lines of code. It would take just a few instructions to configure the PWM and then feed it data.
Yeah, okay. Cool stuff, Chip.
Yeah, if I thought more, I don't really have my head around your whole problem, but if I did, we could probably come up with some cool way to do it that's maybe not anticipated, that doesn't involve so many parts or.
Yeah, well, yeah, I haven't gotten my head around the smart pin modes at all. It's really have to start looking at them and
So Tracy, how come your thing says Thomas Allen?
Oh, that's my first name. I use it for, you know, things like signing up online. And
okay, yeah, that was throwing me off.
Okay.
Tracy, I've written a couple of P2 objects, and one of them is the PWM that you can find online. And as Chip says, it takes about 3 lines of code to set up if you're using spin, which I think you do.
Is it like a duty mode or a fixed frequency PWM that you're talking about?
You can do fixed frequency PWM. There's, like Chip was saying, there's a 16-bit counter that determines, that allows you to set up your frequency. And then you have your duty cycle, which is a percentage of that. It's really straightforward. And there's a command in Spin 2 called pin start, which allows you to set up any smart pin mode. All of the, as Jon Titus was pointing out, the smart pin modes have X and Y registers that are setups. So in pin start, you're going to tell it the pin, the mode bits, which is that 32-bit configuration bits, and Spin 2 has constant names for all those, which simplify them. And then you set up your X and Y values. But if you look up, it's JW underscore, or JM, sorry, I was using my other name, John Williams. JM underscore PWM shows how to do it really, really simply. And it works quite nicely.
That, John, that's a help. I heard from Jon Titus today about the dithered modes too.
Yeah.
It sounds quite interesting to get some of the subharmonic jitter. So that'd be great.
Well, and the great thing is Chip has put into Peanut, which, for compile. And I think that for those that are using Eric's compiler, he has mimicked them, but there are constant names for all of the modes and then the features of the mode. So for example, if you're doing PWM, you select a PWM mode, and you also need to add the output enable bit so you can drive the pin.
Yeah, same as in P1, really. Yeah. Output. Yeah, the whole business with the RC time and pulse width that Roy was talking about really sound a lot like the basic stamp, where you start to measure a pulse width, and you have to wait for that first transition before you you actually start measuring the output, rather than the propeller way, which was just flip the bit and you're already counting.
Well, I think, you're right, because we did, because I used the RC time mode in a couple of analog, wave player modules that I made. And even doing it there, you have to, drive the pin high, give it a bit of time, make sure this capacitor is charged, clear the phase register, and then make the pin an input and wait for the pin to go low. So, you're doing that in code anyway.
Yeah, RC time was like that, but pulse in on the basic stamp, you have to wait for the first transition.
Oh yeah, yeah, good point. Yeah, I was
Roy was talking about sounds like the basic stamp.
Yeah,
project.
yeah.
You know, if you want to measure just resistance or capacitance or say inductance, you can use you can put a pin into like Schmidt trigger mode so it feeds back on itself, or you could use 2 pins. And you could put your capacitive element to ground, or your resistor between them, or your inductor, capacitor, whatever, however you want to configure that thing. And then you can just measure frequency to get your conversion. So it's just always free running. And so as long as you have any kind of, if your sensor's inductive, capacitive, or resistive, you can turn that into a frequency that's just free running in a feedback loop. And then just use like the reciprocal counter to get a really accurate, you know, reading on that in a short amount of time.
Yeah, just to clarify, the RC time thing that I'm trying to implement is from Simple Tools, which is trying to implement it the same way the basic stamp worked. So that is definitely true. And most of the other stuff has been translating just fine. I tried what you said, Chip, and it's still intermittently 0 or always 0, depending on which way I do it. So it doesn't seem to help to toggle the high pin after starting the pin.
All right. Oh, hey, are you doing this? You're doing this in machine language, right? Or assembly?
Well, it's Flex C, so it's getting compiled to hub exec.
There might be some issue because you might just need to put like a couple no-ops in there, because there may be some issue. I mean, it should work by toggling that bit, but maybe the release from reset and the toggling, maybe you need to spread those out by just a few clocks, because there are some latencies as the signals go through registers to get to and from the smart pins. And then the actual real pins. So
okay, I'll try adding a delay.
Yeah, sprinkle some delays between things, and then if it's working, start removing them and figure out which one is critical. There's probably one of them that's critical.
Hello.
Peter, do you have any experience with this kind of thing? Wait, we still can't hear you. I don't think your mic's on.
Coming through.
There we go.
Yep. So yeah. So I just catching up. I'm half distracted here. So yeah, I probably have some experience, and I probably don't. So so what was the question again?
So he has Roy is trying to measure a single slope, right? He wants to measure a fall time of a signal, but all of our measurement things want to see before a falling edge, they want to see a rising edge, right? So he has to fake it out and give it a rising edge. So he can toggle the MSB of the right pin value to invert the pin, but it's not working yet. So I recommended it might be worth trying putting some delays, like a couple, like 3 clock delays between sections, because something might be, the horse might be getting in front of the cart somewhere.
Oh yeah, that's the sort of stuff I do in one line of Taco's code. Yeah, I look, you know, I've played a lot with smart pins. There's a lot of stuff I haven't even had time to. I'd really love to get into it. Can't really help you there at the moment. Sorry.
That's okay.
Hello. Hello. Can I jump in here?
Somebody's trying to talk, but really low input on their mic.
Yeah. Okay. Can you hear me now?
It's getting better.
That's as loud as it's going to get. I don't know if it's going to get any louder. So rearrange things.
I think not enough.
Oh boy. Okay. Let me
Unless it is for you, Chip. Do you hear Gerald okay?
No.
Okay.
Hmm.
And Chip, I pasted in the example I believe Roy is working from too into the chat.
Okay, you mean these questions?
Yeah, this translation of the Propeller.
Okay.
I'm using that sense light as the base, but it's actually the code that's inside of RC Time, which is inside the Simple Tools libraries.
I just comment, Roy, that on, when I first did that using the Propeller one, I found that it was very sensitive to hand waving, near the sensor.
Yeah, so
pick up and through, light variations.
The P1 version of this works perfectly and is very solid. The values are perfect based on how much light it's sensing, and it never gets a 0 unless you aim a bright light right at it. Then it'll get down to it'll be 0, 1, 0, 1, toggling back and forth occasionally. But the P2, it works fine until there's a reasonable amount of light such that the values are below 1,000, and then it just starts randomly putting in zeros in between real values. And I think it's because it's in a bad state for the smart pin. And I'm continuously, just in a loop reading the value and outputting the result, right? So it's just
look
doing
at it
it
on a scope. Do you have a scope you can look at the actual pin?
I have, and the pin is doing the right thing. The pin goes high and drops as expected for each iteration. It's just that the value it reads back is wrong.
Huh.
And I'm pretty sure it's just timing out and then reading in the 0, right?
Yeah, that state machine, for measuring, it's really simple. It's not, there's something we don't understand about what's going on in your case.
Chip, I have a commitment to get to. I'm going to let this Zoom meeting just run so you guys can carry on and let the recording go as well. Okay, so I'm just going to turn on my video stop and thank you, Jon Titus.
Yeah, John.
Okay, I'll post the video later tonight.
Happy to help out anytime. Thank you.
Yes,
Thank you,
thanks,
John.
John. And thanks, Ken, for letting us keep going.
Thank you.
We can talk all night.
I'll have to watch the YouTube of this one, catch up. But the smart pins are, I think we're all trying to work with the smart pins with the documentation, and we can play with it. But the A to D modes are the modes that I really want to play with, and I just haven't had time. But I'll get all this other stuff done and get into it.
Yeah, I'm just scratching the surface, but it's pretty amazing to be able to do in a single smart pin command stuff that would take a whole cog program running on the P1 and consume a counter, right? Now you can do it in a single pin, and you can just set the pin up and you don't even need a cog running, really. You can just occasionally check the state of the in thing and read your result, and away you go.
Well, yeah, for, the pins have current drive modes, right? Like 1 milliamp, 100 microamp, 10 microamp. So if you were to put a pin into a Schmidt mode, right? You'll see, and you have some variable capacitor. You'll see the slope is completely triangular. It's not this kind of thing. It goes and it falls and it goes up and it falls. It'll be just like triangle pattern because the current sourcing and sinking will be constant for whatever setting you set. So it's a way to linearly translate capacitance into a number. And all you do is set the pin up to oscillate, and then you you know, have a smart pin measure the period in the simplest case, or have it count up like 10 periods. There are modes which can count an arbitrary number of cycles. So like if you have a very short pulse, you don't want to count one cycle because your granularity is going to be too large. But if you count like 100 cycles of that short pulse, that short cycle, you start to get a much more accurate reading.
I'm going to try that out right now, Chip. Right now. My cap here. Put it in.
What's that, Peter?
I'm going to try that out right now. I can just type a one line just to say go to 100 microamp mode and do that for me, please. And while you're talking, that's fine.
And you could, if you have a scope nearby, and if you have a capacitor, you could put on the pin. You can see this triangle wave pattern, the triangle shape.
Yeah, I'll do that. The cap in there, right? Right out on here. See what we get out of it. The pins up on here, make it a bit easier.
There are other things, while he's setting that up, you can use pins like a pin pair as actually kind of an op amp or something where you feed back. And you can do it with, you know, you can compare two pins and feed back the opposite or the true of the disparity through some circuit, which might be might go to a FET gate or a bipolar base, and you can feed that back through and maybe use a level comparator, if not an AB pin comparator. So you could make voltage amplifiers, power supplies, all kinds of stuff, but we haven't really documented that much yet, but it's all very simple. It's in the low level pin configurations. And for the PWM, you gonna say something, Peter?
So I'm just typing in the line here now. I've got it hooked up, but we've got 100 microamp source, and I've got 100 microamp sink. I'm just going to go high low. Yep, that's it.
You know, use the let's see. Use a Schmidt trigger. Like the pin A Schmidt, and then like where the first 4 bits are 0100, and then invert or set the O bit, and then set HHH and LLL to like.
Yeah, I've got all those described, so I only have to type the name in.
Okay.
So, but I'm just double checking my setup here. I'm getting some kind of slope up here. I'll just check to see what it's doing.
I could do this here too if I had I could find a captator.
I just grabbed a little through-hole cap I have here. Okay, this is what I'm getting out of it at the moment. I'll just swap this around. Okay, so that's what I'm getting out of it there. Go low. Go high.
Yeah.
Yeah, that's a 0.1, you know, cap that just happened to be floating around here. I'd put on there. It'd probably do better with this with a different type of cap, I'd say. You know, one of the polys instead of the ceramic. Yeah, because the ceramics you're going to get, you know, you're going to get problems there. won't be very linear, but if I get a small NPO or polycap, might look a bit better.
Yeah, and then put it into Schmidt mode so that it feeds back on itself, and then it will just oscillate.
Yep.
Let's see, CIO. So,
Yeah. Sorry for the noise, I'll mute that. Clocked in, converted in and out. If I've got a Schmidt mode defined in there at the moment, I'll have to put one in. I have to find the documentation on that.
oh, here we go. Oh, my camera doesn't go that far. But anyway, that's.
Yep, oh, beautiful.
And this is the code that did it.
What value cap do you have sitting on there at the moment, Chip?
I don't even have a capacitor. It's just open loop, but I selected the 10 microamp drive, which is very weak.
Oh, okay.
Whoops.
I'll do a 10 microamp. Source on that one. Microamp 6.
So if we had, oh yeah, see if I touch my finger to it, let's see. Can you see my finger too? What if I go like this?
Ah, very good. See it all that.
Anyway, now that that thing is oscillating on its own, you could put a smart pin on that too and have it just measure. In fact, you know what? I'll do that real quick. I'll just say, let's see, the mode that I want is, I want to measure, I want to time cycles. Time A states, time A highs. Time X A input highs, rises, edges. Here we go. So I want to measure 100. Those things are like, 8 microsecond cycle. So let's measure 100 of those guys. And then okay, and this is let's see here. I'll set up a scope. Oh boy, need my docs here. Well, actually, I'll just print it out first. Read pin.
That Schmidt mode there, Chip. What's the code for that Schmidt mode there?
Let's say that again. Sorry.
Okay, so I haven't got the documentation in front of me. I'm just looking up. I haven't have the Schmidt mode defined. I've got a lot of the other modes defined.
Let's see.
I'm cheating at the moment. I'm just doing timing it 200 microseconds high and low with a 10 microamp source. I'll just change it over to a 1000 picofarad ceramic. So, anybody know the mode for the Schmidt mode on there? I haven't found it yet.
Oh, no problem, Wes. Here we go. The thing about smart pins is tricky. There's a lot of details that you need to remember to make it go. So I have mine now, let's see. So there I have, you see that readout and that little program?
Yep.
So as I put my finger near this thing, let's see, to increase the capacitance, it goes up quite high and then comes down. Now I could put this on a graphing scope. So I just get my hand near it, it actually changes too. People might be getting bored out there and dropping dead.
Staying with you.
Guys still alive? Stephen Rocco still alive?
Oh, yeah.
We're still with you, Chip.
I'm still here. I'm just trying to get this to work.
Hey, I always enjoy watching people work and play. That's the way I learn the most, guys.
Yeah.
See how you're thinking about it?
Okay, so if I set scope and call it SC,